All right, so we are going to jump back to U-substitution. So this is like, I don't know, I think the 4th day we've spent on U-substitution. So I called it 4.5D. I don't really know. But we need to go back and look at definite integrals with our U-substitution, okay? So I'm going to start with a pretty low-key example, and we're actually going to do this example twice. Okay. So some of you can kind of see why this is a low-key example, right? Especially since we had a warm-up problem that was pretty similar. The pieces to the puzzle for U-substitution really come together quite nicely for this one. Now, before we go through this, I just want to remind you about when we look for U-substitution opportunities, okay? U-substitution is used when we have some sort of a composition of a function, okay? So like, you know, sine squared times cosine. Sine was inside of the square, and then it was multiplied to cosine, which helped us with our du. X squared plus 1 is inside of the 50th power, and there was something extra on the outside that helped us with our du, okay? Remember yesterday we talked about rewriting integrals, like if we're multiplied or dividing, it is possible to rewrite. That's definitely an easier way to go than trying U-substitution. So don't automatically just go to U-substitution. Definitely think through our other strategies first. But this one right here that I had you write down, you do not want to take x squared plus 1 to the 5th power. Okay, that is a waste of your time. Okay, so let's talk about what we would do for U-substitution. In this case, very similar to our warm-up problem, you would probably let u equal x squared plus 1, which means du is 2x dx. So here's the thing. These limits of integration, 1 and 3, they're attached to when we're using x's. So if we're going to use U-substitution, here's way number 1. What we're going to do is we're going to rewrite our integral, but just write it as an indefinite integral. So this would be u to the 5th, 2x dx becomes du. So I'm just going to ignore 1 and 3 for a moment. Then we can take our antiderivative to be 1/5 u to the 5th. Wow, Mrs. Holman. Actually take it 1/6 u to the 6th. Okay. Now I'm going to go back to using my x's. So I'm going to write 1/6 x squared plus 1 to the 6th power. And now I'm going to jump back and bring in my limits of integration. I need to actually evaluate this from 1 to 3. Correct. Okay, so I took kind of a timeout and just did my U-substitution antiderivative. Then when I brought it back to x's, I also brought back my limits of integration. Okay, so now the fundamental theorem of calculus tells us that we need to take 1/6 times plug in 3 minus 1/6 times plug in 1. Oh, there we go. Okay, and luckily I have some charts over there to help us out, right? Okay, so we have 1/6 times, is that 10 to the 6th? Yeah. Okay. Like that. Minus 1/6 times 2 to the 6th, 64. All right, what is that? I'll let you use your calculator. Number. I think it's a nice number, actually. Where would you get? 166,656. Nice number. Not a fraction. That's nice. Okay. So that is option number 1 when working with the definite integral with U-substitution. Okay. Option number 2, we are going to do the exact same problem. We should get the exact same answer. Okay. But this time what we're going to do is we're going to actually change the limits of integration to reflect the u's. And if we do that, we won't ever have to go back to x's. Okay. So if we say that u is x squared plus 1 and du is 2x dx, then we're going to change every single piece of this integral. So this is going to become the integral u to the 5th 2x dx becomes du. But then we're also going to change our limits of integration. So these are x's. This is x is 1, x is 3. Okay, I'll just write that, kind of obnoxious. Okay, so we can come over to here and we can figure out what u would equal and change our limits of integration. So let's see, if x is 3, then when we plug that in, u is going to be 10. That number should be familiar from before. Okay, if x is 1, then when we plug that into u, we get 2. So now we just have the integral from 2 to 10 of u to the 5th du, and we no longer have to worry about x anymore. We've done the switch. Okay, now all we need to do is take our antiderivative and evaluate it from 2 to 10. I feel like it's the same amount of work either way. Okay. In this one, you do a little bit of calculating and then a little bit of more calculating when you get to the fundamental theorem. The other way, all of your calculation is coming when you apply the fundamental theorem of calculus. Okay. What I'd like you to do is just have a quick conversation with your buddy and kind of just process through which one did you like better and why. Three very short. Yeah. Like they get like short unit 5, but and then unit 6. And then it's not as much. Okay, so just curious, how many of you, in the words of Reagan, are vibing with the first way? Second way? Wait, could you raise your hands a little bit higher? The first way. The second way. Awesome. It's like almost 50-50. Okay. Let's go through another example. But this time we're going to look at when our integral maybe doesn't have everything it needs to inside and we have to make an adjustment. Okay. So this looks like a composition where I have 4x cubed plus 1 inside of the fourth power, and it's really convenient that we have an x squared outside of it, isn't it? Okay, remember we kind of talked about those patterns. If we're going to do U substitution with a polynomial, having that one less power on the outside makes it really nice. Okay, so we could let U equal 4x cubed plus 1, which would mean du is 12x squared dx. Well, I see x squared dx in my integral, not 12x squared dx. Yes, we need to divide this 1/12 over with the du. So now we have an exact replacement for our x squared dx. Okay, so now our integral is going to become 1/12 du replaces the x squared dx, and then we'll have, I don't know why I wrote it so far away, u to the fourth inside. Okay, now I'm going to go ahead and change the limits of integration. If that's not the way you want to do it, move on ahead without me. All right, when x is 1, it looks like our u would be 5. So this bottom limit is going to change to 5. If x is 2, then it looks like our top limit would be 25. No. Sorry. This is a 4 right here. This is a 4. So this would be 33. I definitely took 8 times 3. Okay. So now when we do our antiderivative, we have 1/12 times 1/5 u to the 5th evaluated from 5 to 33. 12. Where'd my 1 go? There we go. Whew. So we have, oh man, 1/60th times 33 to the 5th minus 1/60th times 5 to the 5th. Okay. Now, I'm not going to make you do this in your head in like a quiz situation. Okay. So if a problem like this were on the quiz, I would let you use your calculator, but I would have to see all of this work. Right. So first of all, when you punch this into your calculator, what do we get? You got 6, 5. What? Is that what you got? Okay. Now, let's check our work. Try the Math 9 command. The Math 9 command with this up here. We do our math correctly? Whew, okay. A little nervous about that number, weren't you? Very original. Always go back to the original for the Math 9. All right. I now have one I would like you and your buddy to work on together. Oh no. Not oh no. All right, here it is. You and your buddy work together. Make sure we get the same answer. And we'll continue. So you would need to put it in parentheses. So like you're going to go over here.
Yeah. You to the 1/2 you and your integral. Yeah. Sorry. No, it wouldn't be. I'm gonna do it. That's not.
I'm thinking this one should be nicer numbers to work with. Not really. Not really. They match.
So
All right, let's start talking about this. Okay. Evan G, what did you let U equal? Which means du was 2x dx. So when you rewrote your integral, Ruby, what would we write? Good. And if you changed your limits of integration, then you would have 1 to 2. Kind of boring. Right? So then our antiderivative should be 1/2 times u to the 3/2 times 2/3. Those go away. Evaluated from 1 to 2. So we have 1/3 2 to the 3/2 minus 1/3 1 to the 3/2. So if you didn't have a calculator, you would have to pretty much leave it like this. Okay. Now, with your calculator, it is fine to approximate this to be 0.609. Okay. Did you figure out what happened? Okay. But on a non-calculator, you would have to leave it like that, which is fine. If you have something irrational, we can't add it to a rational number, so we just keep them separate, and it's awkward, and it's fine. All right, the last concept I want to talk about before we take a break for our quiz review tomorrow is the concept of average value. The average value. So now we have to keep straight average rate of change versus average value. What's in red is the most important, okay? What's in black is just basically the fundamental theorem of calculus applied to it, okay? Yes.
The big F is the antiderivative.
Correct. Correct. Big F is the antiderivative. Big F, little f. Do you have a question or is this a stretch? Okay. So I want us to think about this in terms of my velocity example that I gave yesterday. Okay, why does this mean average value? Okay, well, first of all, if you look at this, it's average, an average, right? But when we think of like yesterday when we were talking about velocity and position, okay, if we take the antiderivative from A to B of velocity, right? Then we get our position at B minus our position at A. So we're talking about like a distance here, right? Well, if we divide it by B minus A, like the amount of time that took, if we take a position and divide it by time, what do we now have? We have a velocity, okay? So by dividing by B minus A is essentially what this is. By dividing by B minus A, when we're talking about like units, right? We're back to that original. Let's think of it in terms of area under the curve, okay? If we're talking about the integral from A to B of f of x dx, that's area, right? Well, then when we divide by our stretch of x's, we're now taking 2 dimensions, dividing it by 1. Now we're talking about the average y value, or the average value of our function, okay? That's what's happening when we add this extra divide by b minus a, okay? We're taking the 2-dimensional area, dividing by the stretch of x's, so now we have an average of what our y height would be, all right? Go ahead and write this down. Okay, so now we're going to have to be a little bit careful with our vocabulary words. Average value of a function is involving the integral divided by b minus a. So we're going to take 1 over 3 minus 1 times the integral from 1 to 3 of 3x squared minus 2x dx. And this represents the average value. What is the average y value on function from 1 to 3? That is what we're finding. Okay. Bless you. Okay, so we have 1/2 times, well, I really chose a pretty nice function, didn't I? Our antiderivative is just x cubed minus x squared. Is that really all it is? From 1 to 3. Okay. Okay, let's talk about this. What is 3 cubed minus 3 squared? $18? Okay, so we have 1/2 times 18 minus 1/2 times, oh, 0. Don't need to write that down. So we have 9 for our average value.
The 1/2 up front, you don't need the over whatever. Your B minus A, that is your B minus A.
That is the b minus a. Yep. And I sometimes you'll see people write this as a fraction, like they'll take their entire integral, blah, 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 and write it over b minus a. I don't really love the look of that. Okay, if you want to do that, that's fine. I like to just move it out in front as a fraction coefficient because I feel like it's just easier to work with and it doesn't get in the way. Some of you are kind of OCD about, you know, the line that you use in your notebook. Okay, so this way would help you with that. All right, doesn't take up as much room, I guess. Okay, so I think your homework tonight comes from 2 different pages. Okay, one of the pages will be all of the U-substitution stuff, but then average value is from a different portion of the book. So just pay attention to that. Okay, if I were you, I would definitely get caught up on your homework tonight if you're missing some assignments. Tomorrow, I feel like we're really going to need to work on Riemann sums again. So that is going to be like the in-class work that we do before I give you the worksheet is going to be about Riemann sums. So maybe even like take a glance at that at the beginning of class so you're like reminded of how to do that.